positive nucleus, negative electron. And remember, the farther they get from the nucleus, the less energy it takes. And then you can go to the periodic table and identify this element. In our last lesson, we talked about effective nuclear charge and the force of attraction between an electron and nucleus. This time we're going to talk about ionization energy. So let me define that for you. I like to abbreviate IE. I abbreviate a lot. Don't you do that. You follow your instructor. But ionization energy is this: the energy it takes to remove an electron from a nucleus. Now, what is the attractive force that holds it? It's those Coulombic forces that we talked about. Positive nucleus, negative electron. And remember, the farther they get from the nucleus, the less energy it takes. So it depends on their location. So let's look at what we call photoelectron spectroscopy, or you may see it as PES in your textbook. So imagine a machine that we could add some energy to, let's say some megajoules per mole. So if we could add energy and then we would just dial it up, and as soon as we reach that magic energy that would remove the valence electron, the outermost electron, it would just fly off. Okay, and so as we came to those electrons, we could remove them as we dialed up the energy, and then we could kind of collect the data of at what energy did those electrons come off. This is really the printout. So take a look at this example. Now, if you notice, I've got a scale here that really, there's a break in the scale. It's not to scale. I like to mark my zero there. Now, this is going to be a clue of what element this is based on the energy at which the electrons came off. So where would the electron require the least amount of energy? Close to the nucleus or far? It would be far from the nucleus. So the one closest to the nucleus, I'm going to write my nucleus down here. I like to put this. So I know that the electrons closest to the nucleus would require the greatest amount of energy, even though it kind of looks backwards on this scale. So what orbital is closest to the nucleus? The 1s orbital. So I know that the first two electrons, 1, 2, remember the height here shows the number of electrons. This represents my 1s orbital. So I've got 2 electrons in the 1s. All right, and then farther from the nucleus requires less energy. So this next peak, notice it's the same height, same number of electrons. What's next? 2s. The next peak is really tall. Let's see, if that's 2, 4, maybe 6 electrons, what orbitals are next? The p electrons. Remember, they hold 6 electrons. And then look at my last peak. This is a really small amount of energy far from the nucleus. It looks like the same height as my first peak, so I'm going to assume that in the 3s there are 2 electrons. And then you can go to the periodic table and identify this element. This is magnesium. And we can see these are the ionization energies that it takes to remove each electron. How cool is that? Okay, so the guy closest to the nucleus required a lot of energy, and the electrons far from the nucleus required a small amount of energy. Let's do another one. Take a look at this guy. Let's see if we can write the electron configuration. Well, first I have to figure out which end is the nucleus. Well, here's my 0 mark, and ionization energy is increasing to the left. And so closest to the nucleus, it's going to be right here. I'll just put some protons in there so you can recognize the nucleus. So what orbital do we come to first? It's got to be the s orbital, so that height would represent 2 electrons. So 1s2. The next one is 2s, right? And that looks like the same height, so let's go with, 2s2. And then the next orbital available is the 2p. Now how many electrons? Well, if that's 2, that looks like 3. So let's go with 2p3. Can you figure out that element? Well, add up those electrons, right? 2 plus 2 plus 3 is 7. So this is nitrogen.